Earth's crust, the very ground beneath our feet, is thinner than an apple's skin if you were to shrink our planet to that size. It is a startling thought that everything we know, every mountain, forest, and ocean, exists on such a fragile, delicate shell.
It certainly is, Mia. That analogy really drives home the scale. On average, the continental crust is only about 30 kilometers deep, and under the oceans it is even less, perhaps 10 kilometers. Beneath that incredibly thin layer lies the mantle, a vast region of slowly flowing rock that makes up the majority of Earth's volume.
So we are essentially floating on these fragile rafts, as the source material describes it, adrift on molten currents. How do rocks like granite, which feel so utterly solid to us, fit into this picture? The text says granite once flowed like molten rivers. It sounds almost contradictory.
It is a testament to the immense pressures and temperatures deep within the Earth. Granite starts as magma, molten rock, gathered in subterranean chambers. Over millions of years, this magma cools and crystallizes very slowly underground. That slow cooling is what gives granite its characteristic speckled texture of quartz and feldspar. When you touch granite today, you are touching the cooled remains of that ancient fiery flow, frozen in time. Many of our most iconic landscapes, from Yosemite to the Scottish Highlands, are essentially solidified, ancient magma.
And the idea of something flowing like liquid, then hardening, brings to mind diamonds. The source notes that while most diamonds take billions of years to form, some can apparently form in a heartbeat. How does something so seemingly stable and ancient have such unpredictable formation times?
It is all about the conditions. Most diamonds, as you say, are born from carbon deep within the mantle, subjected to immense heat and pressure over eons. But under the most extreme specific pressures, carbon can rearrange its atomic structure into diamond almost instantly. These sudden transformations happen miles beneath the surface, where temperatures are hotter than molten metal. When volcanic eruptions bring these gems upward through what we call kimberlite pipes, they carry a story from Earth's deep creation, whether they formed slowly or in that geological heartbeat.
So, from rocks that solidify over eons to crystals forming in an instant, the Earth is dynamic even in its core. And it is not just internal. Mountains, those symbols of permanence, are described as still rising, even faster than our fingernails grow. How can something so massive be in such constant, measurable motion?
It comes back to those thin rafts of crust we discussed earlier. Mountains are formed where tectonic plates collide. In places like the Himalayas and parts of the Andes, that collision is still happening. The Indian plate is pushing into the Eurasian plate, forcing the rock upward a few millimeters each year. So while erosion from wind, water, and ice is constantly tearing them down, the forces deep below are rebuilding them in a relentless cycle. If you could speed up time, you would literally see them breathe, swelling upward as continents collide.
It is remarkable to think of something as fixed as a mountain as a part of a much larger, restless journey. And this journey is not just limited to individual peaks. The text says entire continents float like rafts on molten rock. Is this concept of continental drift truly happening at a noticeable pace?
Absolutely. The ground beneath us drifts on the mantle, which behaves like an incredibly slow-moving liquid. The continents are immense rafts of rigid stone sliding and colliding at rates of a few centimeters per year. While that sounds slow, over millions of years, these tiny movements reshape the entire world. Oceans open and close, mountain ranges rise, and climates transform. Australia, for example, is drifting north toward Asia at a few centimeters every year. And our planet's surface recycles itself through plate tectonics, meaning nothing on the surface is permanent. It is an endless process of destruction and renewal.
So the continents we know are just temporary configurations in this cosmic dance. The text points out that the ocean floor is surprisingly young compared to the continents. Why the significant age difference?
The ocean floor is constantly being renewed. Along mid-ocean ridges, molten rock rises, cools, and forms new crust that slowly spreads outward. As it drifts, it eventually sinks back into the mantle at deep ocean trenches, melting to become part of the Earth once more. This recycling means that no ocean crust lasts longer than about 200 million years, which is a fleeting moment in Earth's history. The continents, by contrast, are ancient survivors that largely float above this cycle of destruction. The oldest continental rocks are billions of years old.
That explains the difference in age. And this process of seafloor spreading leaves behind a fascinating record, doesn't it? The magnetic stripes on the seafloor that record Earth's ancient magnetic field reversals, like a planetary barcode.
Precisely. As new crust forms at mid-ocean ridges, minerals within the lava align with the planet's magnetic field before they cool. If the field reverses, the next band of cooling rock aligns in the opposite direction. By reading these alternating magnetic stripes, scientists can trace the history of magnetic flips over tens of millions of years. This discovery was crucial evidence that confirmed the theory of plate tectonics and seafloor spreading. It shows that beneath the oceans lies not chaos, but a perfectly ordered record of the planet's invisible forces, written in stone by magnetism.
It is incredible how these rocks act as silent historians. Speaking of silent forces, the source mentions that every volcano on Earth connects to a hidden magma chamber, beating with molten fire. But how long can these subterranean infernos actually persist?
Some volcanic eruptions are not just explosive events, they can be patient and relentless, flowing for hundreds of thousands of years. We call these flood basalts. When mantle plumes release massive amounts of magma, it can bury entire regions beneath miles of solid rock. The Deccan traps in India or the Siberian traps in Russia are enormous relics of such ancient fire. During their reign, they released enough gas and heat to alter the planet's climate and change the course of life itself. These reservoirs remain hidden, slowly refilling and evolving, constantly reminding us that glowing worlds of molten stone lie quietly below.
So, beneath what appears to be a stable surface, there's this immense, long-term fiery activity. What about the immediate dramatic manifestations of this internal heat? What makes basalt, for instance, cover most of the ocean floor, and what are those pillow lavas that sound so unusual?
Basalt is the most common rock type on Earth. It is a dark, dense rock born of fire when molten material from the mantle erupts along mid-ocean ridges and cools quickly in contact with seawater. It forms the vast, unbroken crust of the ocean basins. Pillow lavas are a specific formation of basalt. When lava erupts underwater, it cools so rapidly that its outer layer hardens instantly, while molten rock still pushes from within. This creates rounded shapes resembling pillows or bubbles stacked on each other. Each pillow is a snapshot of fiery motion frozen in an instant, showing how molten rock interacts with cold seawater. Finding pillow lava on land tells us that area was once deep underwater.
That makes perfect sense. So, basalt forms under the ocean. What about the rapid cooling of lava on land, forming obsidian?
Obsidian is volcanic glass. When lava cools so rapidly that crystals do not have time to form, it solidifies into this natural glass. It is smooth, sharp, and reflective. It is essentially molten fire arrested mid-motion, with heat transformed into fragility. For millennia, humans have prized it for tools and ornaments because of its perfect, sharp edges. It stands as a dramatic contrast, born in violence, yet perfectly still and fragile.
It is fascinating how such different materials can originate from the same basic process of cooling lava, just under different conditions. Moving to another kind of record keeping, the text mentions rocks preserving bubbles of Earth's ancient atmosphere. How is it possible for something as ephemeral as air to be trapped in stone for millions of years?
It is truly remarkable. Within the tiniest hollows of certain rocks, particularly in ancient lava or sedimentary layers, scientists have discovered microscopic bubbles of air. These are like time capsules, sealing the chemical signature of the atmosphere from ages past. By studying them, researchers learn about the gases that once filled our skies, oxygen levels, carbon dioxide concentrations, and how volcanic activity or early life altered the balance. Each bubble contains an echo of an ancient breath, a ghost of the air that once surrounded ancient forests or early life forms.
So, holding such a rock is literally holding a fragment of vanished sky. It connects us so directly to our planet's deep past. And speaking of deep, vanished places, the source mentions mountains higher than Everest hidden beneath the sea. It is hard to imagine such immense structures remaining largely unseen.
The mid-ocean ridges are colossal chains of volcanic mountains stretching for tens of thousands of miles, rising higher from their base than Everest does above sea level. They are the most active regions on Earth, with lava continually emerging, building new peaks and valleys. The tallest of these hidden giants, like Mauna Kea, when measured from its base beneath the sea, actually surpasses the great Himalayan summits. They are a constant reminder that much of Earth's grandeur lies unseen beneath the waves.
That is a truly mind-boggling scale. And then we have the deepest point, the Mariana Trench, nearly as far below sea level as planes fly above it. This isn't just a low point, is it? The material suggests it is an engine of renewal.
It absolutely is. The Mariana Trench, with its Challenger Deep reaching nearly 7 miles beneath the surface, marks a subduction zone. This is where one tectonic plate slips beneath another and sinks back into the mantle. This process recycles crustal material, feeding it back into the Earth's interior. So while it is the lowest point on Earth, it is also a critical part of the planet's continuous renewal, reminding us how vast the hidden world beneath the surface truly is.
These extreme depths, the constant motion of mountains and continents, it all points to a planet that is far from still. The text even says the planet hums with micro-earthquakes we never feel. It sounds like a constant, imperceptible vibration.
That is precisely right. Even when the ground appears utterly still, thousands of tiny quakes ripple through the crust daily, too small for us to detect. These micro-earthquakes release small bursts of energy as Earth adjusts to stresses deep below. Scientists use sensitive instruments to record these whispers, mapping shifting faults and magma flows. This ceaseless trembling tells geologists where faults are creeping, where pressure is building, and where volcanic systems are stirring. The stillness we perceive is truly an illusion. The planet is in constant motion, sighing and cracking in slow, secret rhythms.
And sometimes those subtle movements become dramatically overt, like when earthquakes can make entire rivers run backward. That seems utterly impossible.
It is rare, but it can happen with powerful earthquakes. When the land tilts or shifts abruptly, it can temporarily force rivers to reverse their flow. The Great New Madrid earthquakes of the early 19th century, for example, caused sections of the Mississippi River to temporarily flow upstream. The sudden movement of the crust can raise one side of a fault or drop another, creating natural dams or changing the gradient. These moments reveal the sheer strength of geological motion, showing that even something as constant as a river can be turned backward by Earth's deep forces.
So the ground is not just moving, it is almost alive, with rivers occasionally defying gravity. And then there are faults that creep silently, without any shaking at all. How does the Earth relieve pressure without the drama of an earthquake?
That is fault creep. Along certain sections of faults, the crust slides so slowly and evenly that there is no noticeable shaking at the surface. This quiet movement relieves pressure in small, continuous increments. It is invisible to us, but measurable by instruments detecting motion of just a few millimeters per year. This subtle dance between tension and release is part of the planet's constant balancing act. It reminds us that even without drama or noise, the ground beneath us is shifting, whispering in slow motion as Earth adjusts itself grain by grain across the ages.
It is all happening right beneath us, and even deeper, at the very center of the planet, the core is hotter than the surface of the sun. This immense heat is obviously fundamental to all these processes, isn't it?
It is the driving force. Temperatures there reach over 9,000 degrees Fahrenheit, rivaling the sun's surface. This heat is leftover energy from Earth's formation, combined with the decay of radioactive elements deep inside. It drives everything from volcanic eruptions to the magnetic field that shields life from cosmic radiation. The inner core, which is solid iron, rotates slightly faster than the planet, while the outer layer flows in liquid form. This hidden furnace is Earth's beating heart, powering its movement, warmth, and resilience.
And there might even be an entire ocean hidden deep inside the mantle, according to the text. Not an ocean as we know it, but water trapped within minerals. It is a staggering idea.
It is. Scientists have found minerals containing vast amounts of trapped water hundreds of miles below the surface. This hidden reservoir could fill the world's oceans multiple times over if released. It is not free-flowing water, but bound within crystal structures. The movement of tectonic plates may carry water downward into this realm, only for it to return through volcanic eruptions. This unseen cycle could be key to understanding why Earth has oceans at all, showing that water finds a way to endure even in the deepest stone.
Water, then, is everywhere, even in the deepest parts of our planet. And speaking of deep, hidden wonders, the text describes crystals growing larger than a person inside underground caves, like the Cave of the Crystals in Mexico. How do these immense structures form in such specific ways?
The Cave of the Crystals holds translucent gypsum blades stretching over 30 feet long. These grew over hundreds of thousands of years in perfect stillness, nourished by hot, mineral-rich water that once filled the chamber. The conditions required are incredibly rare, a delicate balance between heat, saturation of minerals, and immense time. When the water drained, the crystals remained gleaming. They are geology's most beautiful expression of stillness, shaped entirely by time, proving that even the hardest materials can move and change with enough patience.
So it is a process of immense patience, yet the growth rate of cave formations is even slower than fingernails. That is an almost unfathomable slowness, isn't it?
It is. Stalactites, flowstones, and crystal draperies accumulate one layer at a time as water leaves behind thin films of mineral. A single centimeter of growth can take hundreds of years. The rate depends on the water drip, mineral purity, and temperature. These formations are living records of the cave's history, tracking changes in water chemistry and climate. They are subterranean sculptures that remind us that beauty can emerge not from speed or force, but from stillness and persistence beyond human measure.
These deep, slow processes are truly remarkable. And then there are salt domes, which can pierce through rock like slow-motion explosions. It is hard to picture salt behaving in such a forceful, dynamic way.
Salt, though solid, behaves like a viscous fluid under immense geological stress. In regions with thick layers of ancient salt buried beneath heavier rock, the salt slowly flows upward, pushed by pressure from surrounding layers. Over millions of years, it can bend and break the rock above, forming dome-shaped structures miles high. These salt domes can even trap oil and gas, creating important reservoirs. They are vast pillars of slow movement, reshaping the earth in silence, a testament to ancient seas that evaporated long ago.
It is another example of how solid ground can behave in ways we do not immediately imagine. Another seemingly solid thing that has a fluid past is petrified wood. It looks like wood, but it is stone, atom by atom. How does that transformation occur?
When a tree is buried by volcanic ash or sediment, groundwater seeps into its cells carrying dissolved minerals. Over thousands of years, each tiny structure of wood is replaced molecule by molecule with quartz, preserving every ring, knot, and fiber in perfect detail. The result is a fossil that looks like wood, but is cold and heavy to the touch. Sometimes trace elements color it in vibrant hues. It is nature's way of showing that nothing truly disappears, it only changes form, keeping the story of life locked within stone.
It is a beautiful way to preserve the past, and it makes me think about other fossilized remains, like coal and oil. The text says coal began as ancient forests and oil from ancient plankton. This links geology directly to biology and energy.
That is absolutely correct. Long before humans, vast tropical forests, when they died, sank into oxygen-poor swamps where decay slowed. Layers of plant matter built up, and over millions of years, heat and pressure transformed this organic material into coal, a dense rock of concentrated carbon. Similarly, for oil, microscopic life in ancient oceans died, sank, and mixed with mud. Over millions of years, heating and compressing transformed their carbon-rich remains into liquid hydrocarbons. Every piece of coal and every drop of oil holds the energy of ancient sunlight, stored for eons, linking present energy to Earth's deep past.
So, in essence, we are burning ancient sunlight when we use these fossil fuels. It is a powerful connection. And on a much smaller scale, every grain of sand tells the story of a vanished mountain. How much history can a tiny speck of sand hold?
Each grain of sand once belonged to something far greater. It was part of a towering mountain or an ancient bedrock plain. Over millions of years, wind, water, and ice ground that rocked down to its smallest pieces, carrying them across rivers and seas. A single grain might have tumbled through glaciers, flowed down canyons, or drifted across oceans. Under a microscope, its shape and composition reveal its origin and journey. Every handful of sand is a storybook of time, a collection of broken worlds reduced to glittering fragments that will one day be pressed back into stone and start the cycle again.
That is an elegant way to put it, a storybook of time. And speaking of sand, the idea of desert sand singing with a low musical note when it moves is just mesmerizing. Is this a common phenomenon?
It is rare, found in deserts like Morocco, Chile, and the Arabian Peninsula. The sound, a deep, resonant hum, comes from countless grains sliding and colliding in unison, vibrating at a specific frequency. Scientists believe the grains must be nearly uniform in size and perfectly dry for this effect. Travelers describe it as haunting, as though the dunes are breathing or speaking. It is physics and friction turning the landscape into a natural instrument, singing the slow, patient music of the shifting earth.
What an incredible natural concert. And beaches themselves come in so many surprising colors. The text mentions black, green, pink, and even red sands. It seems like a beach is never just a beach, does it?
Not at all. Each color tells a geological story. Black sands often line volcanic islands formed when molten lava met the sea and shattered. Green beaches appear where rare minerals like olivine from deep within the mantle wash ashore. Pink hues come from crushed shells and coral, while red sands are tinted by iron-rich rock oxidized over time. Walking these colorful shores is like wandering through the planet's palette, with every wave rearranging grains that carry the memory of fire, water, and time, blending the world's elements into natural art.
It is like the Earth is painting with its own history. And glaciers, those massive rivers of ice, also carve landscapes like moving rivers of rock. They seem so still, yet they are such powerful sculptors.
A glacier flows even though it appears still. The weight of accumulated snow compresses into dense ice that slowly slides downhill, reshaping everything in its path. These frozen rivers grind against mountains, scraping valleys, polishing stones, and carrying debris. When they retreat, they leave behind wide U-shaped valleys and shimmering lakes. Their fingerprints are on nearly every continent, from Yosemite to Norway. Even now, they continue their patient work, grinding ancient rock into fine dust. They are sculptors of continents, artists of time and temperature.
And some glaciers move fast enough to be seen shifting by the hour. That is truly astonishing for something so massive. It defies our perception of ice as purely static.
It does. While most creep inches per day, a few surge when meltwater lubricates the ground beneath them, reducing friction. In Greenland and Alaska, glaciers have been documented racing ahead at surprising speeds, their surfaces groaning and cracking. From a distance, it looks impossible, solid ice behaving like liquid stone. But this movement carries enormous power, reshaping valleys and transporting rock by the ton. It is seeing time itself accelerate, the slow rhythm of the Earth condensed into a visible, breathtaking surge.
So it is not just water and wind, but also ice, reshaping the planet. And the concept of fossils preserving not just bones, but even raindrops that fell hundreds of millions of years ago, or soft tissues in colors. It seems to defy what we typically think of as fossilization.
These are rare and delicate forms of preservation. For raindrops, delicate impressions can form on soft mud, quickly buried by new sediment layers before hardening into stone. Each tiny crater records a moment in time, a storm passing over a primeval landscape. For soft tissues and colors, certain conditions, like rapid burial in fine sediments and mineral-rich water, can replace organic molecules with stone before decay. This preserves skin, muscle, and feathers, sometimes with traces of pigment. These fossils bridge worlds, allowing us to feel the echo of warmth and color from beings that vanished hundreds of millions of years ago.
It is almost like a ghost in the stone, showing us a past that is much richer and more detailed than we might have imagined. And the very beginning of life's impact on Earth is visible in stromatolites, the oldest known life forms, recording their history in layered structures.
Stromatolites are essentially layered structures built by mats of bacteria that trap and bind sediment in shallow seas. Some ancient examples are over 3.5 billion years old, making them among the earliest evidence of life. Remarkably, stromatolites still exist today in a few remote places, like Shark Bay in Australia. They show us how life's story began not with motion or complexity, but with patience, with microbial communities slowly turning light, water, and time into the very foundation of everything that followed. They literally record the oldest known life on Earth.
So life started simple, but had a monumental impact. And speaking of monumental, the idea of a snowball Earth, where the entire planet was covered in ice, then being thawed by volcanoes, sounds like a truly epic planetary drama. Was this a unique event?
It was indeed epic. Around 700 million years ago, Earth nearly froze solid, with ice stretching from pole to equator. For millions of years, it was a vast, silent world of ice, but volcanic activity continued, pumping carbon dioxide into the atmosphere. With the oceans sealed under ice, the gas could not dissolve as usual, so it built up, trapping heat. Eventually, this triggered a dramatic thaw, helping to warm the planet. In a way, volcanoes may have saved Earth, keeping its climate alive beneath the ice. This return of liquid oceans may even have helped trigger an explosion of complex life, showing fire and renewal waiting patiently below, even in the planet's darkest cold.
It is astonishing how intertwined geology and life are, and it was ancient microbial mats that first made oxygen in the air, so the very air we breathe is a gift from these tiny, ancient organisms.
Absolutely. These microbes, ancestors of modern cyanobacteria, lived in shallow seas billions of years ago. They used sunlight to split water molecules, releasing oxygen as a byproduct. At first, this oxygen reacted with iron in the oceans, forming vast deposits of rust-colored rock, what we call banded iron formations. Only after these minerals were saturated did oxygen begin to fill the atmosphere, slowly turning it into the life-giving mixture we depend on. This great oxidation changed everything, allowing complex cells to evolve and paving the way for all plants and animals.
It is a profound thought that every breath is a connection to those ancient microbes. And those banded iron formations you mentioned, the text says they mark the moment the planet began to breathe, so they are literally the planet's first breath recorded in stone.
They are. These bands of red and gray rock shimmering with metallic luster are the fossilized record of when oxygen first appeared. As primitive microbes produced oxygen, it reacted with dissolved iron, forming rust-like minerals that settled to the seafloor in layers. Over millions of years, these sediments hardened, capturing the breath of a newly awakening planet. Each stripe in the stone is a heartbeat in Earth's transformation, marking the slow transition from a world without air to one alive with oxygen.
And before oxygen, the seas were purple. That sounds like something out of a science fiction novel, a completely alien world on our own planet.
Indeed, before oxygen filled the air, Earth's oceans may have shimmered with shades of red and violet. These colors came from ancient microbes that used sulfur, not oxygen, to capture sunlight. These organisms thrived in chemical-rich seas under what might have been an orange sky, producing pigments that tinted the water. As photosynthetic bacteria began releasing oxygen, these purple oceans slowly faded to the blue we know today. The shift from a sulfur world to an oxygen one was one of the greatest transitions in Earth's history, altering everything.
It is incredible to imagine our world looking so different, and this constant reshaping extends to entire mountain ranges vanishing without a trace. It really underlines the impermanence of even the most massive features.
Absolutely. Over deep time, wind, water, and gravity patiently wear down even the tallest peaks. Erosion can erase a mountain as easily as waves smooth a pebble. The roots of ancient mountains sometimes survive as crystalline rock buried beneath newer layers, but the surface expression is gone. Earth is always rebuilding itself. What seems eternal to us is only a temporary sculpture in the ongoing art of geology. Every plain and valley was once a summit, and every stone carries the ghost of a vanished mountain.
And this leads us back to the grand ballet of continental drift. The continents have collided and split apart many times, creating what the text calls the supercontinent cycle. It is a much longer and more complex story than just Pangea.
Yes, Pangaea was only the most recent supercontinent. Before Pangaea, and even before Rodinia, Earth assembled and broke apart at least half a dozen times, forming vast supercontinents like Nuna, Columbia, and Pannotia. Each had its own mountains, oceans, and climates. Their formation and breakup altered the course of evolution, stirring the climate and shifting deep ocean currents. The continents we know are pieces of those ancient giants, survivors of a cycle that spans billions of years. To study them is to read Earth's autobiography, where even the land itself is temporary.
So Pangaea was just one chapter, and it seems the next supercontinent may already be forming under the Pacific. What clues suggest this future monumental event?
Scientists predict that in 200 to 300 million years, the continents may converge again. Some models suggest the Pacific Ocean will close as Asia and the Americas move together, forming a landmass sometimes called a meisha. Others imagine the Atlantic closing. Though the outcome is uncertain, the process is inevitable. The same invisible currents that tore Pangaea apart are still at work, shifting continents inch by inch. The Earth is always remaking itself, and somewhere deep below, the first motions of the next supercontinent have already begun.
It is a staggering thought that our maps are so temporary, and the process is ongoing even now. Africa, for example, may one day split into two separate continents, which is a truly dramatic prospect.
Deep within East Africa, a great rift stretches for thousands of kilometers, marking where the continent is slowly tearing apart. Volcanic activity, earthquakes, and thinning crust reveal that a new ocean may eventually form there. In a few tens of millions of years, the region, including Ethiopia, Kenya, and Tanzania, could separate from the rest of Africa, drifting eastward. Lakes like Tanganyika and Malawi fill the rift's deep scars, early clues to the ocean that will one day flood in. It is like glimpsing the birth of a future continent.
So the rifting process we see in Africa is similar to how the Atlantic formed. And Iceland sits directly above a tear in Earth's crust, literally growing new land. It is a live demonstration of these forces.
Iceland straddles the mid-Atlantic ridge, where two tectonic plates are moving apart. Molten rock wells upward through this long tier, building new land as it cools. The entire island is a crossroads of fire and ice, with glaciers beside active volcanoes. Hot springs, geysers, and lava fields testify to the restless energy below. Iceland is one of the few places where this boundary rises above sea level, allowing scientists to study the raw mechanics of plate tectonics in plain view. It is a living experiment of creation, where the Earth literally grows before our eyes.
It is a truly unique natural laboratory, and Yellowstone hides one of the largest volcanic systems on Earth, a supervolcano that can alter the planet's climate for centuries. We are living above immense power, aren't we?
We are. Beneath Yellowstone's geysers lies an immense magma reservoir. Its past explosions reshaped much of North America, scattering ash across entire continents. While not expected to erupt anytime soon, supervolcanoes release thousands of cubic kilometers of ash and gas, blocking sunlight and cooling the globe for decades or centuries. These titanic eruptions cause volcanic winters where temperatures drop and ecosystems struggle. They remind us of the delicate balance between Earth's interior and surface, and how such power has shaped evolution itself.
It is a humbling thought, how these geological events can reset the course of life on Earth. And the largest known volcanic eruption at Lake Toba in Indonesia is said to have influenced early human populations. The scale of these events is hard to comprehend.
Around 74,000 years ago, Toba expelled over 2,000 cubic kilometers of ash and magma, leaving a caldera 100 kilometers wide. The blast darkened skies, lowered global temperatures, and some scientists believe it caused a brief volcanic winter that impacted early human populations. Even after the eruption, volcanic gases lingered for years. Today, the tranquil lake seems peaceful, but beneath its calm waters lies one of Earth's most powerful scars, a reminder that the planet's greatest moments of creation often come wrapped in destruction.
And the ash from these eruptions can circle the globe for years. It is another way geology connects us all through the atmosphere.
Fine volcanic ash can drift in the upper atmosphere for years, carried by winds. Particles from major eruptions like Pinatubo or Krakatoa have been detected long after the events. They scatter sunlight, producing brilliant red sunsets and slightly cooling global temperatures. Some layers of airborne ash even return to Earth centuries later, discovered in ice cores and ocean sediments. Every eruption, no matter how remote, connects to the atmosphere that wraps the entire planet, carrying traces of distant ages.
It is a beautiful image, the echoes of Earth's fiery breath tinting our skies. And then there are lava lakes that can remain molten for decades, like windows into the planet's heart. These are not common, are they?
They are rare, found in a few volcanic craters like Ala in Ethiopia and Kilauea in Hawaii. Molten rock never solidifies here, sustained by constant heat and magma from below. Their surfaces churn and ripple like fiery oceans, crusting over only to break apart again. At night, they glow like windows into the planet's heart, flickering against dark rock and smoke. They can persist for decades, offering scientists insights into magma that cannot be replicated in labs. Each lake is a reminder that Earth's fire still burns just beneath its thin, cooling crust, timeless and alive.
And the explosive power of volcanoes is truly elemental, even to the point of generating lightning inside ash clouds. That must be a spectacular sight.
It is. The immense friction between ash particles creates powerful electrical charges. As these charges build, they discharge as lightning bolts that crackle through the ash plume. Volcanic lightning can illuminate entire skies, creating storms of fire and light above erupting mountains. Unlike ordinary thunderstorms, these flashes are born entirely from the energy of rock and gas. Scientists study these flashes to understand ash flow and eruption intensity, as lightning can signal how violently material is being ejected. It is the fusion of Earth's elemental forces, solid, liquid, and gas meeting electricity, a brief and inspiring display.
It is such a powerful demonstration of Earth's raw energy, and it becomes even more dramatic when volcanoes meet ice, creating explosive steam eruptions. I imagine Iceland has a lot of experience with that.
Iceland's volcanoes often behave this way. When magma rises beneath glaciers, it melts huge volumes of water instantly, producing steam that expands with explosive force. These eruptions can blast through the glacier, sending floods and ash clouds cascading down valleys. The interaction leaves behind unique landforms called tuyas, ridges and plateaus sculpted by fire and water together. It proves that even the most opposite elements of nature are connected in a cycle of creation and transformation, reshaping our planet since its earliest days.
And this creative force is so strong that entire new islands have risen from volcanic eruptions within living memory. It is incredible to witness the birth of new land.
Submarine volcanoes occasionally erupt with such force that they build islands from the seafloor upward. In the past century, eruptions near Iceland, Japan, and Tonga have created fresh patches of land. Some vanish quickly, eroded by waves, while others grow stable enough to host life. These newborn islands reveal a planet's creative power unfolding in real time. To watch one form is to witness the process that built continents long ago. It reminds us that Earth is not finished with its work. The planet continues to build, break, and begin again.
It is a dynamic planet indeed, but some of its features are quite unsettling, like lakes filled with dissolved carbon dioxide that can erupt like soda. That sounds like a silent but deadly threat.
They are indeed a rare but powerful phenomenon called limnic eruptions. In parts of Africa, certain deep lakes contain massive amounts of carbon dioxide trapped beneath their surfaces. When the balance of temperature or pressure changes suddenly, that gas can burst upward in a deadly, invisible wave. Lake Nyos in Cameroon released such a cloud in the 1980s, tragically suffocating life in nearby valleys. Scientists now monitor these lakes as it is a stark reminder of how even tranquil waters can conceal immense energy, originating from volcanic sources below.
That is a truly terrifying natural event. And then sinkholes, which can swallow buildings in seconds. It is a reminder of the fragility of the ground beneath our feet.
Sinkholes form where limestone or salt dissolves slowly in underground water, creating hidden cavities. When the roof of one of these voids collapses, the ground above drops away suddenly. Some are meters wide, others hundreds across, devouring cars, trees, and homes without warning. They often form after heavy rain, which weakens the layers below. Though dramatic, sinkholes are part of Earth's natural recycling of rock, where water patiently sculpts the landscape from beneath, revealing the fragile balance between solid ground and hidden hollows.
It is a constant, quiet transformation, and karst landscapes, with their secret rivers flowing through stone, showcase this water sculpting power on a vast scale.
Where limestone or dolomite bedrock dominates, rainwater carves intricate networks of tunnels and caverns stretching for hundreds of kilometers. These underground systems carry entire rivers beneath the surface. Water disappearing into a cave entrance might re-emerge miles away as a clear spring. Karst landscapes provide drinking water for millions and are found on every continent. Exploring them is like entering the circulatory system of the planet, where stone and water move together in endless dialogue, dissolving, shaping, and renewing the surface of the Earth drop by drop.
And within those caves, we find the incredible formations of stalactites and stalagmites, growing from ceiling and floor to form pillars. They are sculptures of unimaginable patience.
Indeed, dripping water carries dissolved minerals, which slowly crystallize as it evaporates. From the ceiling, each droplet leaves a tiny ring of calcite that lengthens over centuries, forming the stalactite. Where drops land, matching mounds grow upward as stalagmites. Eventually, they can meet to create towering columns. This process is so gradual that growth rates are measured in millimeters per century. These formations are living records of the cave's history, tracking changes in water chemistry and climate, creating what looks like forests of stone.
It is such a beautiful reminder that beauty can emerge from stillness and persistence. And the fact that earthquakes can permanently change the length of a day, even if only by microseconds, is a truly profound connection between deep geological forces and the rhythm of our daily lives.
It is a measurable effect. When a massive earthquake shifts the distribution of Earth's mass, the planet's rotation subtly changes. By moving enormous slabs of rock, an earthquake can slightly alter the planet's moment of inertia, similar to a spinning skater pulling their arms inward. After the 2004 Sumatra earthquake, scientists calculated the day shortened by fractions of a second. These shifts remind us that even the concept of a day, which feels absolute, is influenced by the deep movements of rock and gravity. Each quake is not just a surface event, but a planetary one.
And the shockwaves from massive quakes travel all the way around the globe. It means the entire planet rings like a bell, transmitting energy through its core.
Seismic waves from powerful earthquakes ripple outward through the entire planet, racing through rock and mantle. Sensitive instruments can detect the same quake echoing around the world multiple times. The largest quakes make the entire Earth tremble, subtly flexing its crust. Scientists use these global reverberations to map the planet's interior, tracing how waves bend and reflect inside molten layers, revealing where it is solid, fluid, and how heat moves. Every great quake briefly turns the world into a single vibrating instrument, humming softly with its own heartbeat.
It is a constant, subtle hum, and the energy released in some of these quakes is staggering, equivalent to millions of tons of TNT. It is difficult to even imagine that scale of power.
When the largest faults rupture, they release as much power as several million tons of explosive material detonating at once. The shaking we feel is only part of it. Most energy travels deep, moving rock layers that weigh more than entire mountain ranges. The moment magnitude scale was designed to measure these immense forces. The 2011 Tohoku quake in Japan, for instance, released enough energy to alter the planet's rotation and shift the seafloor by meters. Each quake reminds us that Earth's crust is under constant pressure, storing and releasing energy in a powerful rhythm.
It is a relentless cycle, and the idea that rocks deep underground can flow like putty under pressure is another one of those counterintuitive geological truths.
Though stone feels unyielding to us at great depths where temperatures and pressures rise beyond imagination, rock deforms slowly, flowing like an extremely thick liquid. Over millions of years, this plastic movement allows entire mountain ranges to rise, fold, and melt into new formations. The mantle beneath our feet constantly moves this way, its flow driving continental drift. It is a reminder that even what seems rigid is capable of motion, and that the strength of stone lies not only in hardness, but in its ability to yield, reshape, and endure.
So even the most solid things eventually yield to immense time and pressure. And metamorphic rocks then record this history of pressure and heat inside the planet. They're literally the Earth's diary pages, aren't they?
They are. When rocks are buried deep, immense heat and pressure reorganize their minerals without melting them entirely, creating new textures and structures. Granite becomes gneiss, limestone becomes marble, shale becomes slate. Each metamorphic rock carries a record of the forces that shaped it. Scientists read these records to reconstruct ancient mountain-building events or the depths at which rocks once rested. When exposed at the surface, they show us the planet's internal history frozen in crystalline form. They are stones that remember, preserving the immense energies that flow invisibly beneath the crust.
It is a profound thought that every rock tells a story. And then there are the gemstones. The text says every gemstone tells the story of its geological birth. They are not just pretty rocks, but concentrated packages of geological history.
They truly are. Diamonds form under crushing forces hundreds of kilometers down. Emeralds grow in mineral-rich veins where water and rock exchange elements. Rubies, sapphires, topaz, and quartz each arise from precise conditions of temperature and chemistry that rarely coincide, making them precious. When cut and polished, their clarity reveals the harmony of their atomic structures, a glimpse into order forged in chaos. Each gemstone is a messenger from a different environment within the planet, a record of its hidden processes. To look into a gemstone is to peer backward into Earth's memory.
And the fact that rubies and sapphires are the same mineral, colored by different elements, really highlights that precise chemical story.
They are both varieties of corundum. In its pure form, corundum is colorless. When tiny amounts of chromium enter that structure, it glows red and becomes ruby. When iron and titanium take its place, the result is blue sapphire. Other trace elements produce yellows, greens, or pinks. These subtle substitutions in atomic makeup change how light passes through the crystal, giving each gem its hue. It shows how small changes at the atomic level can yield astonishing beauty, a fingerprint of chemistry.
It is truly nature's artistry, and opal, which is so unlike other gemstones, forms from ancient groundwater seeping through silica rock. It sounds like something born of a slow, delicate chemical dance.
Opal is unique because it isn't crystalline. It forms when water-carrying dissolved silica trickles through rock, depositing microscopic spheres that stack in delicate layers. These spheres scatter light, producing opal's characteristic rainbow shimmer, the play of color. Many opal deposits began in arid landscapes that were once wet millions of years ago. As water evaporated, it left behind these intricate, glowing structures. Every opal captures not only the light we see, but the memory of vanished rain, lost rivers, and the quiet chemistry that turns water and sand into fire frozen in stone.
It is a beautiful thought, but geology also connects us to the cosmos, with meteorites on Earth telling stories from before our planet was born. What kind of stories do these cosmic visitors carry?
When fragments of rock fall from space, they bring messages from the earliest days of the solar system. Some meteorites formed billions of years ago, long before Earth, from the same cloud of dust and gas that birthed the sun and planets. They contain minerals that have remained unchanged since that time, preserving a record of ancient chemistry. Scientists study them to learn how planets assembled. Some even carry organic compounds, hinting that ingredients for life were scattered through space long before Earth began to form. To hold a meteorite is to touch something older than our world, a piece of cosmic debris carrying the memory of creation itself.
It is like holding a piece of the early universe in your hand, and within these rocks, some grains are even older than the solar system itself. Pre-solar dust, it is called.
Yes, microscopic grains called presolar dust are remnants of ancient stars that existed before the sun. These tiny crystals formed in the outer layers of dying stars and were carried into space by stellar winds. They drifted through the galaxy for billions of years, eventually becoming trapped in the material that built our solar system. Their isotopic fingerprints reveal their alien origins, different from anything found naturally on Earth. When we analyze these particles, we read stories written before the sun rose, echoes of supernovae, and the slow breath of red giants. Each grain is a whisper from the galaxy's past, proof that Earth was born from recycled stars.
So we are all literally stardust, and lunar rocks brought back by astronauts helped date Earth's early crust. How did moon rocks inform us about our own planet?
The samples from the Apollo missions revealed secrets about Earth's beginnings. The isotopic composition of lunar rocks matches Earth's mantle, supporting the theory that the moon formed from debris after a colossal collision between a young Earth and another planet-sized body. By studying those rocks, scientists estimated Earth's crust first solidified around 4.5 billion years ago. Some lunar basalts also record impacts that shaped the early solar system, preserving a record of ancient bombardment lost on our eroded planet. Every moon rock is a time capsule connecting two worlds linked by a violent origin story.
It is a powerful cosmic connection. And speaking of dating Earth's early history, the oldest minerals ever found are tiny zircons from ancient Australia, which even record the first liquid water on Earth. That is a fundamental discovery.
These microscopic zircon crystals found in Western Australia date back over 4 billion years. They formed soon after Earth itself, surviving countless cycles of erosion. Inside each, uranium decayed into lead, allowing precise age measurement. Their composition shows liquid water existed on the planet when they formed, suggesting Earth's surface cooled surprisingly quickly after its violent birth. This pushed the timeline for Earth's oceans much earlier than thought. Each zircon, smaller than a grain of sand, is a microscopic archive of water's arrival on Earth, glimpsing a world where vapor condensed and the first drops of rain fell.
It is a tiny crystal holding such an enormous history, and Earth's history also includes periods where continents were covered in lava fields the size of countries. These truly massive flood basalt eruptions.
Throughout deep time, enormous volcanic events blanketed vast regions in sheets of molten rock for millions of years, forming plateaus thousands of meters thick. The Deccan Traps in India and the Siberian Traps in Russia are dramatic examples. Such eruptions released immense volumes of gas, altering climate and ecosystems. When they cooled, they left behind stepped rock landscapes and rich soils. Standing atop one of these regions means standing on frozen lava that once flowed in rivers of fire, rewriting continents. Earth's calm present hides a fiery past.
And those lava floods have caused mass extinctions in the past. It sounds like a truly catastrophic force.
The gases and ash released during flood basalt events could poison the air, darken skies, and disrupt climate for thousands of years. The Siberian Traps eruption 250 million years ago coincided with Earth's greatest extinction, wiping out most marine species and many on land. These catastrophic releases of carbon dioxide and sulfur dioxide triggered acid rain and global warming, unraveling ecosystems. Yet in the aftermath, new life flourished, adapting. These cycles of destruction and renewal are woven into Earth's story, reminders that even devastating events become foundations for what comes next.
In every extinction lies the seed of evolution. It is a powerful idea. And ash from ancient eruptions still lies buried in modern soils, nourishing new life.
Across the world, thin layers of volcanic ash are preserved within sediment and soil, silent records of eruptions thousands or millions of years ago. Each layer can be traced to its source volcano by unique chemical signatures, building precise timelines. Farmers sometimes unknowingly work these ancient ashes into their fields, enriching the soil. In places like Italy, Iceland, and Japan, volcanic deposits have made the land extraordinarily fertile. The same ash that once blotted out the sun now nourishes crops and forests, completing a cycle where destruction feeds creation.
It is a continuous cycle of life and death, destruction and creation. and the Atlantic Ocean was once just a long rift valley. It is hard to picture it as anything but the vast expanse it is today.
Before the Atlantic, the land that became Africa and the Americas was joined in a single supercontinent. Deep cracks began to open between them about 200 million years ago, forming a vast rift that filled with water as the continents drifted apart. Over millions of years, volcanic activity widened the gap, and a new ocean was born. The mid-Atlantic ridge, where new crust still forms, marks that original separation line. Ancient rift valleys like those in East Africa offer glimpses of what the early Atlantic looked like, proof that immense seas start as narrow wounds in stone that slowly deepen.
So a wound becomes a world, and the sea spreads outward from the mid-Atlantic ridge like a conveyor belt, continuously creating new crust.
In the heart of the Atlantic, new crust continuously forms. Magma rises through cracks, cools, and pushes older rock aside in a steady, symmetrical flow. As this happens, the continents drift farther apart, carried by the seafloor's movement. Magnetic minerals in the cooling lava align with Earth's magnetic field, creating striped patterns that record ancient field reversals. By measuring these stripes, scientists confirmed seafloor spreading and plate tectonics. This underwater conveyor expands the ocean even as old crust is pulled downward elsewhere, keeping Earth's surface in constant living motion.
It is an elegant planetary mechanism, and even in the deepest, darkest parts of the ocean, at these spreading ridges, hydrothermal vents create black smokers and support entire ecosystems without sunlight.
Deep beneath the ocean, seawater seeps into the crust, heats to hundreds of degrees, and rises laden with dissolved metals and minerals. When this superheated water bursts back into the cold ocean, it cools instantly, precipitating dark material that billows upward like smoke. These black smokers are underwater chimneys of mineral and heat. Around them, life thrives, not on sunlight, but on chemosynthesis, where bacteria use chemical energy. Giant tube worms, clams, and crabs depend on these microscopic producers, forming ecosystems unlike any other on Earth. They are a living reminder that even in eternal darkness, the planet breathes, burns, and builds.
It is truly alien and fascinating, and the magnetic field, our planet's shield, has flipped hundreds of times throughout its history. That sounds like a major vulnerability.
The planet's magnetic poles have reversed repeatedly, swapping north for south, sometimes separated by hundreds of thousands of years. The cause lies deep within the molten outer core, where swirling currents of liquid iron generate the magnetic field. As these currents shift, the field weakens, reorganizes, and eventually reverses. Evidence is written in volcanic rocks on the seafloor. While a reversal could take thousands of years, life has persisted through every one of them without disruption. The phenomenon reminds us that even our invisible shield is dynamic, a living force shaped by the movement of Earth's molten heart.
So if it happened today, our compasses would point south, but we would largely be fine. And the moon, our constant companion, stabilizes Earth's wobble, which shapes long-term geology. It is more than just a light in the night sky, isn't it?
Far more. Without the moon's steadying influence, Earth's tilt could vary wildly, causing chaotic climate shifts. The moon's gravity keeps our planet's axial tilt stable within a narrow range. This stability has allowed long-term geological and biological cycles to flourish, providing consistent patterns for ocean currents, ice ages, and weather. The tides created by the moon's pull also help distribute energy through the oceans, influencing erosion and sediment movement along coastlines. Our planet's geological calm owes much to this silent partner, guiding Earth's dance for over 4 billion years.
The moon, then, is a silent architect of our world, and coral reefs, which appear to be living things, are also geological structures made of calcium skeletons. It is a fusion of biology and geology.
Coral reefs are monumental geological formations. Each coral polyp builds a tiny limestone skeleton, and countless generations stack these structures upward towards sunlight. Over thousands of years, the result is a reef so vast it can be seen from space, like the Great Barrier Reef. When corals die, new ones grow atop their remains. These structures serve as natural barriers, protect coastlines, and act as archives of ocean history, recording temperature and chemistry in their layers. Every coral colony is both a biological community and a geological monument, living rock that breathes, grows, and preserves the memory of the oceans.
And some coral reefs are older than many mountain ranges. That is an astonishing thought that something so seemingly fragile can outlast massive stone formations.
Beneath calm tropical seas, reefs have been growing continuously for tens of millions of years. Some began when dinosaurs still roamed. Entire mountain chains have risen and eroded away while these underwater structures quietly expanded. Their cores are compacted limestone from billions of tiny organisms. The endurance of coral reefs shows the planet's continuity through upheaval, their layered skeletons tracing both biological and geological time. Each one is a cathedral of life and stone, older than civilization, older than mountains, a living bridge between eras.
It is a profound testament to biological resilience. And geology even connects deserts to rainforests, with dust from deserts fertilizing entire rainforests across oceans. It is a global circulatory system.
Tiny grains of mineral dust lifted from great deserts travel thousands of kilometers through the atmosphere, carried by winds. Much of this dust falls upon distant ecosystems, delivering vital nutrients. The Amazon rainforest, for example, depends on phosphorus dust blown from the Sahara each year to replenish its soils. Without it, tropical rains would wash essential minerals away. These airborne particles connect seemingly unrelated ecosystems, linking arid wastelands to lush jungles. Each grain is a geological traveler, a fragment of rock that left one landscape to sustain another, in an endless cycle of erosion, wind, and renewal.
It is an elegant system, connecting everything. And our own planet's history is tied to cosmic violence, with gold and platinum coming from ancient meteor impacts. So the precious metals we prize have an extraterrestrial origin.
During Earth's formation, nearly all its gold, platinum, and similar heavy elements sank into the molten core. The metals we mine today arrived later, delivered by meteorites during a period of intense bombardment over 4 billion years ago. These impacts scattered metallic debris across the surface, enriching the upper crust with treasures forged in stellar explosions. Every gold vein or platinum deposit is a cosmic inheritance, the residue of cataclysmic events. To wear or hold a piece of gold is to touch the memory of that ancient rain of metal from the stars, a tangible link between celestial violence and earthly beauty.
It is a humbling thought that our wealth comes from the stars, and the planet is covered in hidden scars from ancient collisions, impact craters so eroded they are almost invisible, yet still influencing our geology.
Over millions of years, wind, water, and tectonic motion can erase nearly all traces of a meteor impact. What begins as a vast circular crater gradually fills with sediment, its scars hidden beneath forests or seas. Yet clues remain in the rocks, shocked quartz, melted minerals, and buried rings of fractured crust. Scientists use satellite imagery and magnetic surveys to uncover these hidden scars. Many once hosted lakes or cities, unaware of their cosmic foundation. The near invisibility of these structures shows how the planet heals itself, slowly smoothing even the deepest wounds until they become indistinguishable from the land.
It is another example of Earth's incredible resilience, and one giant impact may have even triggered the age of the dinosaurs, while another ended it. These cosmic events reshaped life itself.
Around 200 million years ago, a massive asteroid may have struck near what is now Canada, coinciding with the Triassic extinction. The collision released enough energy to darken skies and ignite wildfires. Volcanic activity followed, and global temperatures swung dramatically. Many reptile species perished, while dinosaurs, better adapted, began to dominate. Then, 66 million years ago, a 10-kilometer-wide asteroid slammed into Mexico's Yucatan Peninsula, releasing energy equal to billions of atomic bombs. This impact vaporized rock, ignited global wildfires, and blocked sunlight for years. Photosynthesis collapsed, food chains failed, and over 70% of species vanished, including the non-avian dinosaurs. From that extinction came the rise of mammals and eventually humans, showing how destruction and creation are inseparable.
So Earth's story is one of continuous cosmic impact, shaping its past and present. Even today, space dust adds hundreds of tons of new material each day, making our planet continuously grow, grain by grain.
Every day, tiny particles of cosmic dust drift through space and fall into Earth's atmosphere, burning briefly as meteors or settling unseen onto land and sea. Scientists estimate over 100 tons of this material accumulates daily. Most comes from comets and asteroids shedding fragments. Collectors have gathered microscopic spheres of this interplanetary dust, their metallic surfaces glinting. Over billions of years, such accumulation has subtly increased Earth's mass. These particles are reminders that the planet remains connected to the wider cosmos, continuously exchanging matter with the universe around it, a gentle, ceaseless rain of stars falling upon our world.
It truly brings it all together. Geology links every mountain, ocean, fossil, and living thing in one story. It is the deep memory of our planet, written in stone, always moving, always breathing, always changing.
The study of Earth's history reveals that nothing exists in isolation. The same forces that lift mountains also stir the seas, recycle rocks, and shape the conditions for life. Fossils tell how climate and geography guided evolution, while minerals record the deep processes that sculpted continents. Every river carries the memory of erosion, and every grain of sand once belonged to stone. Over billions of years, the cycles of plate movement, volcanism, and weathering have woven an unbroken story connecting land, life, and time. Geology is the language of that story, the script written in layers beneath our feet. It reminds us that the world is both ancient and alive, an ongoing transformation.
It is a humbling and profound perspective. If you found this exploration of Earth's deep memory insightful, share this episode with someone who would appreciate hearing it.